Tonight, we need to talk about something that most people have completely wrong. When we think about the solar system, we imagine something almost cozy. A bright sun in the center, planets gliding in calm, predictable circles, everything humming along in peaceful order. Diagrams show clean orbits, evenly spaced, everything neatly labeled. What those diagrams never tell you is that the calm we see today is what's left after billions of years of bombardment. Stripped atmospheres and orbital chaos that once had the inner solar system looking nothing like it does today. The solar system is one of the most violent, hostile, and extreme environments you could imagine, and we are living right in the middle of it. And by the end of tonight, you will never look at that diagram the same way again. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The first thing you need to understand is the scale. Because almost everything terrifying about the solar system begins with distance. The solar system is not a small, closely packed neighborhood of planets. It is an almost incomprehensibly vast expanse of emptiness, punctuated by objects that range from quietly lethal to catastrophically violent. Start with the inner solar system. The Sun sits at the center, and 8 planets orbit at various distances. Mercury orbits at roughly 36 million miles from the Sun. Venus at about 67 million miles. Earth at 93 million miles. Mars at around 142 million miles. These are the 4 rocky planets, the ones we think of as the inner solar system. And yet, even within this relatively compact neighborhood, the distances are staggering. The gap between Earth and Mars at their farthest point from each other is over 250 million miles. That is a journey no human has ever attempted. We have sent robotic spacecraft, and the fastest of them have taken roughly 6 to 9 months to cross that void. But the inner solar system is not where the real scale reveals itself. It's when you move outward. Jupiter orbits at about 484 million miles from the Sun. Saturn at roughly 886 million miles. Uranus at about 1,780 million miles. Neptune, the outermost planet, sits roughly 2,790 million miles from the Sun. If you laid that distance out and tried to drive it at highway speed, 70 miles per hour, without stopping, it would take you over 4,500 years to reach Neptune from the Sun. And Neptune is not the edge. Beyond Neptune, the solar system continues for another enormous stretch. The Kuiper Belt extends from roughly 30 astronomical units out to 50 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, 93 million miles. So the Kuiper Belt stretches from about 2,790 million miles to 4,650 million miles from the Sun. And beyond even that, the Oort cloud, a vast, spherical shell of icy objects beginning at roughly 2,000 astronomical units from the Sun, and potentially extending all the way out to 100,000 astronomical units. That outer boundary sits roughly 9,300,000,000 miles from the Sun, and the Oort cloud is considered part of our solar system. Our neighborhood, our home. Something that vast, that empty, that dark and cold is what we are actually living inside. When you absorb that scale properly, the comfortable school diagram starts to dissolve. And what replaces it is something more honest. Something harder to look at without a certain quiet unease. The solar system diagrams you grew up with were drawn that way out of necessity. If you drew the solar system to true scale, with the sun as a circle 1 inch across, the Earth would be a dot smaller than a period on this page, sitting at a distance of about 9 feet from the sun. And Neptune would be a tiny speck, roughly 270 feet away. The Oort cloud, at true scale, would extend for miles in every direction from the center of your diagram. The visualization tools we use to understand our neighborhood systematically and unavoidably mislead us about what that neighborhood actually is. What it actually is mostly nothing. Vacuum, darkness, cold that approaches absolute zero, with occasional islands of matter scattered through the emptiness. Some of those islands are enormous, some are ancient, and some are dangerous. None of them are where the diagrams suggest they are relative to each other. In the true solar system, everything is impossibly far from everything else. Even the planets, which seem so close when drawn on a chart, are separated by distances that would take years to cross at the speeds of our fastest spacecraft. The distances are not the backdrop to the story of the solar system. They are the story. And those distances are full, not empty. Full of radiation, charged particles, magnetic fields, gravitational influence, and billions of objects we have only begun to catalogue. The sun itself is where the terror begins, because the sun is not the gentle golden lamp of popular imagination. The sun is a thermonuclear explosion that has been running continuously for 4.6 billion years. At its core, temperatures reach roughly 27 million degrees Fahrenheit, about 15 million degrees Celsius. The pressure at the core is 340 billion times greater than the atmospheric pressure we experience at sea level on Earth. Under those conditions, hydrogen nuclei fuse together into helium, releasing enormous quantities of energy in the process. The sun converts roughly 600 million tons of hydrogen into helium every single second. Every second. That energy radiates outward through the sun's interior, a journey that takes anywhere from 10,000 to 170,000 years just to travel from the core to the surface. A single photon of light born in the solar core bounces around in the radiation zone for what could be 100,000 years before finally breaking free at the surface and shooting out into space. 8 minutes later, it reaches Earth. The surface of the sun, called the photosphere, burns at roughly 10,000 degrees Fahrenheit, about 5,500 degrees Celsius. That is the cool part. The sun's outer atmosphere, the corona, reaches temperatures of 1 to 3 million degrees Celsius, roughly 1.8 to 5.4 million degrees Fahrenheit. Nobody fully understands why the corona is so much hotter than the surface beneath it. It is a mystery that has puzzled solar physicists for decades. One leading hypothesis involves the energy carried by magnetic waves, called Alfvén waves, that propagate through the corona from below. Another involves small explosive events called nanoflares, which individually release relatively modest energy but collectively heat the corona to extraordinary temperatures. The leading hypothesis shifts depending on who you ask and what the latest observations show. But the heat is real, and its consequences reach across the entire solar system. The solar wind is the sun's atmosphere escaping into space continuously. Charged particles, mostly protons and electrons, flow outward from the corona in all directions at speeds ranging from roughly 250 miles per second to nearly 550 miles per second. These are not particles drifting gently outward. They are a constant, energetic stream of material, blasting through the entire solar system at all times. The solar wind sweeps past Earth, past Mars, past Jupiter and Saturn, past Uranus and Neptune, and continues outward for billions of miles until it finally loses the battle against interstellar space. The boundary where the solar wind becomes too weak to push back against the interstellar medium is called the heliopause. Voyager 1 crossed it in 2012, roughly 11 billion miles from the Sun. That is how far the Sun's direct physical influence extends. 11 billion miles of solar wind. Everything inside that boundary feels the Sun's breath on it, constantly, without interruption. The solar wind is not uniform. It varies in speed and density, forming structures and patterns as it flows outward. High-speed streams from regions of the solar corona, called coronal holes, overtake slower solar wind, creating what are called corrotating interaction regions. These are compressed zones of enhanced solar wind material that travel outward with the rotation of the Sun. When they reach Earth, they can trigger moderate geomagnetic disturbances. They happen all the time. They are routine features of the solar wind environment. But the solar wind is only the beginning of what the Sun does to this solar system. The Sun also produces coronal mass ejections, enormous eruptions of magnetized plasma ripped free from the solar surface and launched into space. A single, large coronal mass ejection can expel several billion tons of plasma. The cloud of material travels at speeds between roughly 90 miles per second and over 500 miles per second. When one of these clouds hits Earth, it interacts with our magnetic field and can cause geomagnetic storms. In mild cases, those storms produce the aurora borealis. In severe cases, they can damage satellites, disrupt GPS systems, create problems for airline navigation, and knock out power grids. The Carrington event of 1859 was the most powerful geomagnetic storm ever recorded. It was caused by a coronal mass ejection of extraordinary size. The storm induced currents in telegraph systems across North America and Europe so powerful that telegraph operators reported sparks flying from their equipment. Some lines reportedly continued transmitting even after being disconnected from their power sources, running entirely on geomagnetically induced current. The aurora was seen as far south as the Caribbean, Hawaii, and Colombia, close to the equator. If a Carrington-scale event struck today, the effects on our technology-dependent civilization would be severe. A study by Lloyd's of London estimated that a repeat event could cause economic losses in the United States alone of up to $2.6 trillion. And these events happen. They are not theoretical. They are a regular feature of the Sun's behavior. Weaker versions occur constantly. A truly powerful one is, in the assessment of solar scientists, simply a matter of time. The Sun also periodically releases solar flares, intense bursts of radiation that travel at or near light speed. A major solar flare can release as much energy as 1 billion hydrogen bombs in a matter of minutes. The X-ray and ultraviolet radiation from a large flare can reach Earth in about 8 minutes. It ionizes the upper atmosphere, disrupting radio communications, affecting GPS accuracy, and in extreme cases can present a radiation hazard to astronauts in space or to passengers on high-altitude aircraft flying polar routes. Solar flares are classified by their peak X-ray output. The largest recorded flare, which occurred in 2003 and was measured by instruments near saturation, has been estimated at class X45. To give that some meaning, the classification scale runs from class A at the quiet end to class X at the energetic end, and within the X class, the numbers go higher with stronger events. An X-45 flare is roughly 25 times more energetic than the largest flare typically considered in hazard assessments. Its effects were mitigated only because the solar active region that produced it happened to be rotating away from Earth at the time. Had it been facing directly at us, the consequences for radio communications, satellite operations, and human spaceflight would have been substantially worse. All of this is coming from our star, the one we think of as warm and life-giving. And in one sense, it is. Life on Earth exists because of the sun's energy. But the same object generating that life-sustaining light is also a continuously active source of radiation, particle bombardment, and energetic eruptions that would be instantly lethal to any unprotected human being. The comfortable distance of 93 million miles, combined with Earth's magnetic field and atmosphere, is what keeps us alive. Without any one of those protections, the story of life on Earth would be very different. The sun's activity is not constant. It follows an 11-year cycle, oscillating between solar minimum, when activity is low and the sun's surface is relatively quiet, and solar maximum, when the number of sunspots, flares, and coronal mass ejections increases substantially. During solar maximum, the frequency and intensity of geomagnetic storms rises. The risk to satellites, astronauts, and power infrastructure increases. The sun reached solar maximum in the cycle that peaked around 2024, one of the more active cycles in recent memory. Several major coronal mass ejections reached Earth during this period, producing auroras visible at unusually low latitudes. No major infrastructure damage occurred. But scientists who study space weather were watching carefully. The margin between a spectacular aurora and a disabling geomagnetic storm can be surprisingly small. It depends on the orientation of the magnetic field embedded in the coronal mass ejection when it reaches Earth. If the field is oriented in a way that reconnects unfavorably with Earth's own field, the transfer of energy into the magnetosphere is maximized. That is when the damage happens. We cannot predict that orientation reliably until the cloud is already most of the way here, which means our warning time for the worst-case scenario is measured in minutes to hours, not weeks, not days, hours. The sun generates an enormous magnetic field that is carried outward by the solar wind. This field, called the interplanetary magnetic field or the Parker spiral, fills the entire heliosphere. It does not extend out straight from the sun. Because the sun rotates, approximately once every 25 to 35 days, depending on latitude, the field lines are wound into a spiral pattern, like water spraying from a rotating sprinkler. This spiral structure extends all the way out to the heliopause, organizing the charged particle environment of the inner solar system into a complex, structured electromagnetic environment. Earth's magnetic field interacts with this larger structure constantly. When the interplanetary magnetic field points in a particular direction, it can link up with Earth's magnetic field in a process called magnetic reconnection. When this happens, energy is transferred directly into Earth's magnetosphere, driving geomagnetic storms. These storms can disrupt satellite operations, interfere with GPS signals, create unexpected currents in long electrical conductors like power transmission lines and pipelines, and expose people at high altitudes, particularly airline passengers and crew on polar routes, to elevated radiation doses. In most cases, the effects are manageable. A satellite goes offline temporarily. A GPS reading is slightly off. Unusual readings in a pipeline monitoring system. But the interplanetary magnetic field does not always interact gently with Earth's field. The Sun's magnetic field flips at the peak of each solar cycle, and during that transition, the field becomes more complex and tangled, with multiple poles appearing simultaneously. During these periods of peak solar activity, the frequency of solar flares and coronal mass ejections increases significantly. And we have built a technological civilization whose most critical infrastructure is vulnerable to the consequences. The Sun is also changing over geological time. Stars of the Sun's type gradually increase in luminosity as they age. The Sun is estimated to be roughly 30% brighter today than it was when the Earth first formed. Billions of years ago, a fainter Sun should have meant a colder Earth. Cold enough that liquid water should not have been able to exist on the surface. But the geological record shows liquid water has been present on Earth for nearly 4 billion years. The resolution to this apparent contradiction, called the faint young sun paradox, involves higher concentrations of greenhouse gases in the early atmosphere, possibly supplemented by other factors not yet fully understood. The point is this: the Sun's output is not fixed. It changes. On human timescales, the change is imperceptible. But on geological timescales, the Sun has already become dramatically more luminous than it was. And it will continue. In roughly 1 billion years, the Sun will be bright enough that Earth's oceans will begin to evaporate. The water cycle will break down. Earth will enter a runaway greenhouse phase, similar to what Venus experienced much earlier in its history. The surface will become uninhabitable. That is not tonight's emergency. But it is a reminder that the star warming us is not a fixed and permanent friend. It is a slowly evolving object with its own timeline. And we exist at a particular, transient moment within that timeline. With that picture of the Sun in mind, we can begin the journey outward. Mercury, Venus, and Mars tell 3 different stories about what can happen to an inner planet. Mercury today has essentially no atmosphere. What remained was stripped away over time by the solar wind. Without an atmosphere, there is no